Hello everyone, welcome to your next section. Today we are going to introduce you to some very basic concepts around statistics. We're going to just kind of introduce you to really the basic things that you need to know when looking at numbers and how to analyze data. We're going to spend this time just kind of showing you, some very first level stuff that you need to know about data and statistics before you go about applying any kind of statistical process to it. However, we will spend a little bit of time showing you some of the very introductory stuff with statistics that you can do in Python in this one, and then in the next lecture go into things a little bit more deep, okay? So with that, guys, let's just jump into it. So today, you're going to learn about the 4 statistical data types, and I'll show you what those are. That's going to be part of your syntax section, and I'm also going to probably just refresh you on what these statistical analysis techniques are called mean, median, and mode. You've definitely encountered at least one, if not all of these in your grade school math, for instance. Okay, so what are we talking about when we talk about data types? In statistics, there are 4 types of data: nominal, ordinal, interval, and ratio. I'm going to spend time talking about each of these in our syntax section and what they mean, but basically you can organize or consider values and information for statistics as one of these 4 types, and it's related to everything else that we're going to do both in this chapter and the subsequent chapters when approaching how to do certain types of statistical analysis, or even visualization for that matter. Next, I'm going to teach you about what the mean is. Mean is basically like an average value. So, if you remember in school, if you have a bunch of tests and you calculate your average, your average test score, that's what the mean is. A median is similar to the mean in that it's also trying to find like a middle number. However, rather than kind of taking an average where you sum up everything and subtract by the amount of numbers, the median is just finding the middle position in your list of values. So there are some positives and negatives towards with that we can read about in like a statistics page like Wikipedia, for instance. And lastly, the mode is the most commonly observed value in a list. So if you have a bunch of test scores and you scored 80% 5 times and everyone else was like a lot less than that, then your mode would be 80. Okay, so let's hop into our syntax here, guys. We're going to play a little bit with how syntax works for these data types, and then do very basic statistical analysis stuff in our coding portion just to show you how all of this comes together. Okay, everyone, so we're going to spend most of our syntax time talking about these data types, but I'm also going to show you a function into how to run like means and medians shortly after at the end here. So when we're talking about nominal, ordinal, interval, and ratio data, we're talking about how information can be categorized and grouped together. So, and each of these kind of extends upon itself. So when we talk about nominal data, we're talking about categories. What's your favorite color? What's your favorite food? Are you male or female? These things have categorical information, but they don't really give you much else. Like, for instance, if you were to compare counting males and females, but also looking at like temperature information, the numbers have more information than just the labels themselves. So when we think about nominal data, we're really thinking about kind of like categorical information. Ordinal data is very similar to nominal data in that it is a category. You have some, like in this example, I'm talking about race position outcomes. So you run a bunch of races and you're getting first place, 5th place, 2nd place. These are still labels. However, each of the labels has some additional information associated with it, meaning that 1 is higher than 2, which is higher than 3, and so on and so forth. You can't necessarily say that black is great or blue is greater than yellow, for instance, with nominal data. So even though these are labels, the positions of the labels actually do have some additional meaning that like 1 is higher than 2. What you can't tell with ordinal data is the distance between these values, i.e. if you came 2nd place in a race and were 20 seconds off this time, but you came second place again later, but you were only 2 seconds off. You were much closer in that second place finish, but you don't know how much of a difference there is between 1 and 2. Like, it doesn't show you how close you got to first or close you got to second. In order to do that, maybe you would do something like time, which is a ratio data type. Interval data has that kind of distance relationship where, you can, like, degrees Celsius is a perfect example, where, you have 21 degrees, and then you might have another value that's 21.5. Well, this one is certainly higher than 21, and we have some basic understanding of how much more it is. It's 0.5 more in terms of this measure. What makes interval data different than ratio data is that interval data does not have a true zero. When we talk about Celsius, for instance, or temperature, you can have like negative 20 degrees. You can also have 0 degrees Celsius, which actually doesn't mean the absence of heat. It just is we placed our value of Celsius at a middle point, and 0 doesn't necessarily mean like true 0 as in an absence. You can have you can get even colder than 0 degrees Celsius. Okay. Ratio data is similar to interval data, but there is a true 0, meaning height. You can have a height of 0. You can weigh nothing. You can have a time of 0, and that actually means nothing exists. So interval and ratio data are often used together, or like the statistical analyses that we use with either of these data types are very similar. So if you have interval or ratio data, your analysis are usually the same. However, with nominal and ordinal data, we tend to use different types of analyses. We use like a rank correlations for ordinal data, and we might use some sort of like ANOVA or some other thing that takes categorical information, maybe a chi-square test or something like that for nominal data. But it's important to know when you're looking at data to analyze, knowing what kind of data it is, A, so that you run the appropriate tests, B, you apply the appropriate visualizations, and C, you understand what the numbers are coming in and coming out. It's really important to understand what your data actually is so you can do your data science on it. The last thing I want to show you here is what we're going to go into a little bit of code with. We are using slightly different syntax for our import right now. Turns out NumPy, which is a number Python package, you're going to learn how to install that right now, is a very useful package, and it has a bunch of like extra functions in it. So this is a very large one, and rather than importing everything from NumPy, we really just wanted the set of functions in this random library, okay? So if we want only specific functions from a large library or a large package, how you go about doing that is you say from this large package, just import this one set of functions, okay? And what random has is this thing called randint, random integer. And I'm asking this random integer function to build a list of random numbers between 0 and 100, like equally random, and give me 50 values. So we would expect that the average for this is going to be somewhere around 50, right? Because we're asking for random integers around that value. Let's hop into our code and start playing with this random integer function so that we can start looking at how we calculate means and medians and modes in Python. Okay, so we're going to move over to terminal. Here we are. We go Python. Oh, first off, make sure that you have NumPy installed. So you go pip3 install NumPy. And mine's installed already, but I'm just going to have it go through. See, it says that it's indeed installed. It is telling me to still update my pip, but if you're getting this as well, make sure you do pip install upgrade like it's recommending. But for now, we're going to hop into things. So we're going to go from NumPy import random. Okay, so it hasn't definitely imported random. So let's do an example. Random.randint 0 to 100 size equals 20. Let's see what it gives us. So we have a new data type. It's called an array data type. Essentially, it's just like a list, guys. Arrays and lists are functionally the same in Python. So you don't worry about how to deal with arrays too much. You feel free to look at the documentation though. So that is how we, call a random set of numbers. I'm going to ask for 50 numbers between 0 and 100, and I'm going to save that in this little X list here. So first thing, let's just look at this. Let's see how many numbers we did get. So we use the length function, and we can check how long this array is. It definitely is 50 numbers long. One thing we might want to do in order to just look at this a little easier is use the sorted function, which will sort a list or an array by, the values that are in it. So you see here, it's sorted all the values from greatest to smallest. We can also go sorted reverse equals true, and it'll give it to you the other way around. So let's just do some quick checks on mean, median, mean, and maybe even median. So first, how do we calculate an average? We sum all of the values in your that you're analyzing, and then you divide by the number of values that are in your list. So we can actually do that without using any fancy packages. We can just do like some base stuff in Python where we get the sum of x divided by the length of x. And we'll see what happens. It returns 49.0, meaning that this is actually close to our average of 50. It did a pretty good job. We can also use, we should probably just import NumPy on its own too. So we're also going to import NumPy, and we're going to check the average using NumPy's function, numpy.mean of x, and what does that produce? It produces the exact same number. There you go. Let's see if we can get it to produce median. It is able to produce median, and if we find the middle value of this list, x, we have 50, so that would be like 24 to 26, right? Oh, of a sorted list, sorted x, will that work? Yeah, there you go. And it would be 20, we would have to go 24 to 27. Anyway, in order to calculate that median, we'd be able to do that no problem, either with the NumPy function or building it ourselves. Regardless of that, guys, that's basically all I wanted to show you for this lecture. I wanted to teach you about data types, the nominal, ordinal, interval, and ratio. I also wanted to just introduce to you some of these basic functions where we're going to produce a random set of numbers and then do basic analysis on it. And then introduce to you NumPy and some of these basic statistical analysis features that we basically apply to every data set I look at. I'm going to calculate a mean to look at some feature, and this is like really the preliminary stuff of statistical analysis. So let's just do a recap. What did we learn today, guys? We learned about statistical data types. We learned about nominal, ordinal, interval, and ratio data. We also learned the very basic tools we use for statistical analysis, which are mean, median, and mode. And going forward, we're going to start using all of this information and applying it in different ways in our next section, where we're going to, start to get introduced to distributions and ways to deal with different types of statistical analysis. So with that in mind, guys, thank you very much, and I'll see you next class. Hello everyone, welcome to your next class. Today we are going to extend our knowledge of statistics and introduce the concepts of variance and distributions, normal distributions to you. So we're going to recap a little bit on what an average is, because averages are really important when we talk about variance and standard deviation. And then I'm going to introduce you to one of the most common probability models that exist. They're called normal distributions. You probably recognize them as bell curves. Another word for them is a Gaussian distribution. So why don't we just jump into it so you can see what I'm talking about with all this. So today you're going to learn about what mean and standard deviation are. Also what variance is as well, because variance is kind of like standard deviation. And then we're going to teach you what the normal distribution is all about and how the dynamics change, or at least the shape of a distribution changes, and the probability of results change given given a different standard deviation or a different mean. So we're going to see how the shape of this bell curve adjusts when we adjust parameters that are used for it. So first off, what is a standard deviation? So a standard deviation is a normalized form of variance. Variance is how much numbers are spread between the average. So if you have an average and all of the numbers are very, very close to that average, you would have a very low variance. They don't vary from the average that much. If the numbers are very spread apart from that average, you would have a high degree of variance. So what a standard deviation is kind of a way of normalizing all of that, so that a standard deviation of 1 always means that a certain proportion of your values are above or below it, okay? So you can think of standard deviation as a form of variance a standardized form of variance that we use to look at shapes of distributions more or less easily. The next thing you're going to learn is what a normal distribution is. So you all know what normal distributions are. You experience them every day, or you probably experience them very often, maybe not every day. But this is the bell curve. This is that common looking bump shape that we see when we talk about school grades and other, a lot of things. So this is the normal distribution was first formalized by a guy named Gauss. So it's sometimes called a Gaussian distribution. And the most amazing thing about this distribution is it occurs everywhere. It's in nature. It's in science. Like we see the normal distribution is one of the most commonly occurring distributions, statistical distributions that exist. So understanding how this distribution works makes it really a lot easier to understand how all the other ones work, because this is such a general, simple, and commonly seen approach to probability and statistics that, it's really the most important jumping off point for understanding this stuff. Okay, so we're not going to have a typical syntax section for this tutorial. Instead, we're going to just look at an interactive graph, an interactive normal distribution, so I can show you how the dynamics of it change. So let's just hop into that now. There it is. That's not it. There we are. Okay, so in this graph, what you're seeing is this is just a website that we've gone to for looking at the normal distribution. I'm going to just scroll down a little bit here. Here is, in fact, what a normal distribution looks like, this blue line. And we have some red dotted lines and some green fill-in shade stuff. You'll also notice that we have these sliding points here that you can play with. So if you want to go to this yourself, you're more than welcome to. So the first thing I want to show you guys is the nomenclature that we use in statistics when we talk about means and standard deviations. First off, this is the symbol we use to describe mean in statistics. It kind of looks like a U with a little thing at the beginning, or a funny shaped M. This is the Greek symbol mu. So when you see this symbol in statistics or any other reading that you do when you're doing probabilities, this means the average. This next symbol here, which looks like an O with a thing attached on the right-hand side of it, this is the symbol sigma. And sigma represents standard deviation, which is like a normalized version of variance. So what I want to do with you guys is play with this interactive graph a little bit. So the first thing I'm going to do is I want to just set this to just some easier numbers. First, if you play with this yourself, you'll see that the shape is changing. That's because I'm changing certain parameters. So what we have here is a graph. We have an x-axis that's going from 0 to 10, and a y-axis that's going from 0 to 1. The x-axis is representing, this could be anything. We don't know what the data actually is, but let's just say for now that it's scores, okay? It's like a test. And the average value, or the average score of a test, let's say it's, out of 10 or something, was 5 out of 10. From this, you can also see we set a standard deviation of 1. What that ends up meaning is how this graph is going to change in terms of its shape. The y-axis here is proportion. So if we had a bunch of people that took this test, what we would say is that at the average, on average, about 40% of people scored an average result. Okay? In normal distributions, what this also means is that 50% or just under 50% of people scored under the mean, and just over 50% of people scored over the mean, okay? And that's what this line sliced down the middle is representing, okay? So if we summed up all of the values to the left of this graph, it would equal 40%, like the amount of people that followed onto this graph. And if we did the same for the right, it would be the same. But we have 50% on either side, okay? That's how this distribution works. So we have a standard deviation of about 1 here. So what that ends up meaning is that once we get to 6 out of 10, about 25% of people would have scored above 1 standard deviation, meaning that 75% of people here scored less than a 6, a standard deviation above the mean, okay? And if we have 2 standard deviations, everything that is to the right of this second dot here would be about like 2.5% to 5% for standard deviation either 2 standard deviations above the mean or 2 standard deviations below the mean. So next I want to play with how variance changes the general plotting and distribution of values within this normal distribution. So what would you expect if I shorten the variance, meaning the values are closer around the mean than if they were a higher variance? So they're distributed more towards the mean. What would we expect to happen to the shape? Would it get flatter or more pointy? Well, it gets more and more pointy as we get closer to the mean. And that's because more people are just scoring in that range and they're not scoring outside of that range. Okay? This is with sigma at about 0.25. What happens if we make the variance larger? Well, this is going to start to flatten out because everyone's getting very, very different scores. And you'll see as it kind of starts to become asymptotic around 5. So this will start to flatten out. Okay, so what this is demonstrating is how variance changes the probability or the distribution of scores around that mean, okay? Now let's just bring that back up to 1. What would we expect if we changed the mu, if we changed our average value instead? Would we expect this to become more pointy, more flat? All it's going to do is keep the shape, but shift where the center is. Shift where, where the top of this value is going to be, okay? And that's just playing with mean there. So, okay, guys, with that, I think we're going to call this at this point. The point of me showing you this was to show you what a normal distribution looks like and how, if you adjust parameters, how that distribution changes, and getting you familiar with these y and x axes, okay? So, what did we learn today? We learned about how standard deviation works, that it's this converted measure of a variance, and that 1 and 2 standard deviations mean that a certain percent of the population should be above or below that score. And that's why the normal distribution is so effective and useful when dealing with, test results, for instance. We then played with the dynamics of this distribution, meaning we saw what happened if we increased and decreased the variance and decreased the average, and how that impacts the shape and how we might actually approach analyzing it.